We start part C of Module 4, Selection Problem. In this part, we will solve the selection problem completely. I already gave you the selection problem before. Actually, we have solved a special case of the selection problem, finding the minimum. So that is the simplest selection problem. In this part, we will solve the general selection problem completely. But the solution is pretty hard, pretty complicated. So I try to go a little slower when I get to the most complicated part. All right, so let's start. First, we look at the introduction. So I try to give you some overall description. First, let's look at the general selection problem. Given an array and a positive integer k. This k we know we want to use, First, the array size still we use n. Array size is n. And the k between 1 and n inclusive. When k equals 1, that means the first smallest element, the minimum problem we did before. But the challenging part is this general k. All right, how to find the kth smallest element? So you can imagine we want to find the kth smallest, but as fast as possible. Everybody can find the kth smallest, right? Everybody. So you can find a method. For example, you just get whole array sorted. Then it is very easy to get a kth smallest. But we want to have the fastest possible algorithm. So that's hard. That's very hard. Here we have a name called this k. We call it kth order statistic. Kth order statistic. So it is its formal name. But there is another commonly used term. It's called rank equals k. Rank number equals k. We count from left. 1 to 3. So rank number increasing from left to right. All right. So now let's do some analysis. First, the data is given unordered. Otherwise, it's trivial, right? If the array is ordered, find the kth smallest. It's trivial. But if it is unordered, then very challenging. Second question, should we solve the array first? Natural question. I mentioned it before. So you may wonder why we just sort it first. Actually, based on the intuition, many students tend to sort the array first. But there is a problem. So let me give you the main reason. It's not a good idea to sort it first, because we know if you sort it first, the sorting cost is big theta of n log n. Why is that? The worst case, average case, or worst case, both? Actually, this average case and sometimes worst case. So to be safe, let's just say average case. Okay? Because the worst case, could be different answers. Average case, so the best we can get is this much. You cannot do better than this. You cannot do better than this. It can be proved. The average case is this. So you have to pay this much to get the array sorted. All right. But the question is, the best algorithm for this problem is better than that. So this is not the best way. The best algorithm can be big theta of n. Big theta of n. Right? Yeah. In this part, we will get this solution. This is the solution. We will find eventually, in this part. All right, so here you can see, here, the situation we have here, you can compare it with an older problem we learned before called element uniqueness problem. Element uniqueness. Unique problem. Do you still remember that? Determine if the elements in a given array are unique or not. In that one, we have one method. We sorted the array first. Then we can get a better solution. The situation is different. In that problem, even we spend this much cost to sort the array, we can get our overall performance improved comparing with without sorting it. But here the situation is different. In that element uniqueness, because if you do not get array sorted, the best solution you can get is big theta of n squared. Big theta of n squared. In that situation, if you get the array sorted, you can improve it to big theta of n log n. So that's better, right? But here, later we will see the best solution we can get is big theta of n, not n squared. In this situation, you cannot sort the array first because this is much worse than this expression. Yeah. So that's the reason. Okay. So you do not sort it. Yeah. All right. So next. This module, divide and conquer, right? So the question is, how do we divide the problem? This is the key of this question. How do we divide the problem? How do we split the array into two subarrays? Subarrays, okay? Yeah. Similar to the binary search, but this time we cannot expect to split it in the median, right? We cannot. So not the element to be split at, so we call it partition element. So that element, in this case, we need to find it, but it cannot be the median. So in general, it cannot be the median. Okay? Yeah. So it is pretty hard to determine that partition element. So we use some pretty complicated method to determine that element. After that, we just call recursive function and get a solution. Okay? Yeah. All right. Let's look at the main idea. Divide the problem into two subproblems. The highest level, but we do not know the detail, so we need to go down, get to the lower level to put a little more detail. Yeah. Drop one of the subproblem. Just like the binary search, after we make the split, we need to drop one of the subproblems. Why you can drop one of the subproblem? Because we can use the rank number to tell us one of the subarray cannot contain this element, then we can safely drop it. Just like binary search, one of the subarrays cannot contain the element to be searched. Okay, yeah, well, all right, next, convert the original problem to one of the subproblems. One of the subproblems. Yeah. Okay, we drop one, the one remains, so that's the size reduction. Yeah. That's our size reduction approach. Yeah. All right, so that's the general idea. Yeah. Still, we need more details. Yeah. Still not enough for our implementation. Yeah. So that is still at a strategy level. So these steps, too abstract. So still at the strategy level. Next, we need to go to the implementation level. Yeah. All right. So here, there is one view I want to point it out. So we may need to use some special property. Yeah. Kth order statistic, right? Yeah. So that's the concept, kth order static. Sometimes we may need to convert it to rth order statistic from right hand side, because kth order statistic we look at from the left hand side. Is it possible sometimes we can look at that same thing, the same element, but from the counted from right hand side? In some special examples, that view is important. Yeah. This view may not be important for our current general problem. In our current general solution, we may not need to use it. But later, I will give you several examples. Try to let you practice elimination method. Very fundamental, very important, but we need to do practice. Yeah. So in that case, then sometimes you may need to use this view. Yeah. All right. Yeah. Next, elimination idea. All right. Yeah. So here I just give you some, mental preparation. Yeah. So when you consider the elimination, there are two cases you can consider. Sometimes, not always, sometimes. One is eliminate from the left end. You count from the left, then you can eliminate a certain number of elements. Then another, so you do some transformation, then you look at from the right hand side, then you can eliminate a few more elements. Yeah. So things like that can help you eliminate as many elements as possible. Yeah. So later, I try to find some example to show you this idea can improve our efficiency. Yeah. All right. Yeah. Here I just draw a diagram. Yeah. Suppose we have an array arranged in this way. Yeah. Sometimes we count number of elements from left hand side, sometimes from the right hand side. Yeah. But we need to know the relationship. Kth smallest is the same as x largest. Yeah. For example, the first smallest element equals, how about nth largest, right? Largest. Right? First smallest equals kth largest. Yeah. Things like that. Second smallest equals n minus 1 largest, and so on. Okay? Yeah. So you get the idea. Yeah. All right. So here, this property, just put somewhere in your mind. Yeah. When you need it, you can use it. Yeah. But for this general solution, we do not need it. We do not need it. Yeah. All right. Yeah. So here we finish our part 1.